So hi everyone, my name is Katty Levinson, and this presentation is called Don't Fix It in Software. And you may be asking what's happening here, and the long and the short of it is, as I just said, I got drunk and mouthed off at DEFCON 17, and someone showed up. The longer story is that somebody showed up when a speaker didn't show up and said, entertain the crowd, and he was whining about how his robot didn't work in software, and didn't work, and he was going to use software to fix it. And the problem was basically that that he said it didn't drive straight. And I'm finally like, "What's the ratio of your drive base?" And he's like, "Are you driving the rectangle with the fat side forward or the skinny side forward?" And he says the fat side. And like, if you look at the nice fat rectangle, I have a laser pointer. This means I'm in charge. If you look at the fat rectangle, if you imagine wheels on the end of this, as you go as you go forward at all, you're basically levering against yourself to walk down, and it's not really magical that you're getting out of alignment. And if you want to only go straight, drive it with the skinny side of your rectangle forward, and then enjoy figuring out how to turn. So this was the situation. And this goes on, more questions, and I wind up doing this very academic, intelligent rant, which I'm really sure probably looked more like that. But the long and the short of it is, afterwards, security comes and takes me aside, and this makes me nervous because I don't have the best history with authority figures. He says, "Why don't you do that? This is a talk." And I was pretty excited because, the bottle of vodka had been offered, and unfortunately some scoundrel absconded with my vodka. I'm really proud I got to use those words. It's like my vocab words of the day. But now, thankfully, someone else will give me vodka. Props to you, dude. But the long and the short of it is, now we're coming up and we're going to do this big list of all the ways in which all the things I wish someone had told me before I started building robots competitively or professionally. At the very least, I can show you some pretty pictures. I do photography, and so most of these slides are pretty pictures. So if I'm really that boring, there's some pretty pictures for you to look at. All right. My best qualification is the experience of doing stuff wrong. As I'm sure you know, all DEFCON speakers are only admitted if they are exceptionally qualified. So that's how things are. These are qualifications I'm probably more likely to put on my resume. Just want to say right now, thanks to Originate, I just started with them a little bit ago, and they're totally like, "Yeah, you can do this talk that's basically self-humiliation. You could do it in our name." They printed me an awesome hoodie, which I unfortunately left on the floor because I plan ahead. But they are awesome, and if you are sick of your boss's shit, consider applying. Basically, if you have a question, just ask, and if we run out of time, I'll have to ignore you, and you can email me. But I'd like this to be, casual and interactive as much as possible. Was what? No. This was DEFCON 17, where I went up and Oh, that sounds terrible. We should do something about that, guys. Q&A afterwards. All right. All right. So the outline, we're going to go through some good ideas, we're going to go through some bad ideas, and we're going to go through some things that people generally just don't think through the whole way. So starting right off with the good ideas. Let's go through physics. Torque is angular force. If you were to take a wrench and apply some force to a bolt in a nice arc, that is torque. Speed is how fast you do it. Physicists will get snobby and tell me that I'm not saying this correctly, and I don't care. This is just a working definition for us idiots, okay? First item is pulse width modulation, abbreviated to PWM. Sometimes you want your robot to be going at a speed somewhere between 0 and int max. People frequently decide that the way to do that is to just feed less energy into the motors, and that's a bad idea. You really should not be doing that. Motors do not output power linearly. You can see this straight line is actually that is the force output. You can see on when it hits the side with the torque, that's called the stall torque. That's where it's not moving at all. Where it hits the x-axis, that is called the free running speed, where there's nothing on it at all. And the variations come in between there. You can see the power that is output in total on the curved line. And you'll notice that like it is not the same at all points. So you actually want to put it where it's getting, I'm sorry guys over there, I'm going to laser this one and try to describe as best as possible, but I apologize in advance. You want to put it, somewhere near the top so you get out as much power as possible and less inefficiencies. All right, so basically you want to pick a good point on that curve and stick with it as much as possible. Gear everything. You know how fast you want the robot to go, so take the motor at the torque and power output you want and just gear it so that the wheels actually turn at approximately the speed you're looking for. And the question is, oh, sorry, nope, we're looking at a picture now. This is an oscilloscope looking at a PWM output. And so you can see that basically the line goes up and down. It's about 1/3 down, 2/3 up. So if you do this insanely fast to humans, it looks like the motor's just running at a slower speed. And so if the line is up 2/3 of the time, it's going 2/3 of its max speed. And this is a real way you control speed on robots without totally messing up your power output. And the question is, how do you pick the point that you run this square wave at? And the important thing to remember is that climbing takes force. Unless you're going to be constantly operating on a perfectly smooth surface, you're going to need a little bit extra boost to get over whatever you happen to run into. And what happens very often is that they put themselves right at this total peak, and then they have to go up a hill, so now they're moving slower, so now they get pushed down this side of the curve, they're outputting less speed, it's coming out as torque, now the motor's less efficient, so they get shoved further down the curve and further down the curve, further down the curve, and they're just wailing in place and really not getting anywhere. So you want to optimally pick a place a little bit over towards the speed side, so if you hit a bump, you don't wind in this horrible downward spiral of getting nothing done at all. And the expected terrain will change approximately where on the speed side of the curve you want to set your running point, generally speaking. Yeah, I hope I'm going at okay speed. This is, you can see at the bottom, these things here. I feel like I'm being a total dick here. These things at the bottom, these are PWMs. You usually do this as a hardware object. You buy them. The internet sells them. They're like $100. They're cheaper if you like fire. But like, a good, trustworthy, I would feel comfortable putting this on my robot, and it will probably not be the thing that catches fire. It's about $100. This guy removed all of the cooling systems because he likes fire. That's his prerogative. You do get to at least see the insides of them, which is interesting to some people. All right, next item. I really shouldn't have to have a whole series of slides on this, but software people think threads are just kind of magic. It's like I've applied a bolt to this problem, and now all my physics are solved. And it's like, no, people major in this shit, and it's kind of complicated. So the once over lightly, this is a bolt. This is not a bolt. Every time you call this a bolt, I die a little inside. And I need to drink. This is a screw. The end is pointy. You don't have to drill a hole first when you put it in. You don't put a nut on the end. So I don't know what this chick's problem is, but you don't need to put a nut on the end of this. Also, bolts need to have something on the other end to hold them on. You either thread the piece of metal or wood or whatever that you're putting them into, or you put a nut on the end. This is wrong. You're just going to rip the head off the bolt here. You see the arrows imply the force? You're going to rip off the head of the bolt, or you're going to rip the twirly... okay. The thread, yeah, we are extremely technical around here. You're going to rip the threads off the screw if you do this. Don't do this, okay? This is also wrong. This is a machine that does nothing but bend your screws. And by screws, I mean bolts. All right. This is going to get a lot interesting really fast. All right, this is wrong. This is also wrong. in this one, you are not bending your bolt, but you're going to shear it because you're using the bolt as the major pieces that keeps it together, and they weren't actually in the same way that, you rip off the head. You'll just shear these things in half. They're like zinc-plated shit. Like, they're really not made for this, okay? Don't do this. This is also wrong. This is, it's Miller Lite, dude. This is right, okay? This is how you do it. The bolt is actually not the object that is holding the pieces of metal together. The bolt is the object that holds the pieces together enough for static friction to take over and actually do your major holding force. It's like you don't, like the force should not be physically in the bolts. The force is in the fact that static, I'm just going to repeat myself. You got it, okay? All right, next, this is a puppy because we're changing ideas. And people say I talk too fast, so I just put puppies and kittens and those things in whenever we have to transition ideas. I hope you guys are cool with that. Puppies are awesome, though, so I really hope you are. Next item, drivetrain ratio. Okay, we're going to consider the places where the wheels, we're going to assume the four-wheeled robot here because we're simple, okay? So assume that the points where the wheels touch the ground are points. You make them into a shape. If it's a square, then you can go forward and turn. If you want it to be super agile, you have the big, like, crazy angle thing, or you drive the rectangle with the short side forward if you just want it to go straight almost all the time. This is not terribly complicated, but a lot of people are just like, I'm making a robot, I'm going to put some wheels on some plywood, So think about this when you're setting up your stuff. Okay, the other thing that people default to is a car. All of you who drive know that cars aren't actually, like, particularly nimble objects. It's just like trying to turn a bicycle. They need to go forward in order to turn. Also, making the wheels swivel properly is a pain in the ass. So unless you have a good reason for this, this is probably not the default that you want to go to, even though it's what you see most often in your daily life. Tank is actually a pretty good default. Just put the wheels down the side, put them all forward to go forward, put these guys forward and these guys backwards to turn. Turns on a dime, pretty clean, it'll scuff up everything. If you care about that, because basically the whole art of it turning is it doing little micro hops. Particularly if you have large tank treads, and then you previously had rug in your house. Some people will do like 2 wheels tank driven and then casters or omni wheels on the front as a slightly less brutal alternative. That will save your carpet significantly, but no guarantees, man. Omni wheels. Unless you have a good reason, you should just buy these. So many people want to make them. I warned you. So they're helpful with the resistance. They permit, like, some people will do, they will have a set of wheels going this way on the robot and then a set of wheels going this way on the robot. And what you can do is by driving different sets of wheels independently, you get a robot that goes this way and goes this way without turning. Cute trick. Terrible lateral traction for pretty obvious reasons. This thing in the middle here is an omni wheel. I'm sorry, the speaker's in the way. I really can't even see that one. I'm so sorry, guys. But yeah, this thing towards the middle is an omni wheel. And as you can see, it's a, yo dog, I heard you like wheels, so I put some wheels on your wheels. These little black things are free floating. So this is why you can have the wheels go opposite ways of each other and not have anything actually fight. This is also the transition side towards vector drives, which are these things with like the miniature hair curler rolling pin things. You'll notice these are at an angle, which means that this wheel, when you turn it, most wheels, when you turn it, they just want to go forward. This wheel wants to go forward and also in the direction of the little hair curlers. And so when you look at this, if you put 4 of them on, their like default state is that they all have they all have 2 directions that they're pushing. And if you balance them right, you actually now have a like fully manipulatable crazy thing. So if you imagine that you drove all these wheels towards this point right in front of the robot here, then they're gonna, what? Oh man, thank you. Awesome, dude. Thank you so much. Fair point, man. Okay, so if you drove all the wheels going towards this way, you'll see that this arrow will balance out with this arrow, and the wheels will actually, and the robot will actually go that way. Whereas if you drove all the wheels towards no. If you drove all the wheels towards this point in the middle, the wheels will all turn inwards, and you're actually going to go up and down this way. It's like kind of sick. Has everyone got that? Okay, people look at me weird when I explain this the first time. It's really sick. Drawbacks. You're losing a lot of power. The robot's constantly fighting itself. Also, if one of your wheels leaves the ground, you are so fucked. It's not even funny. This is not an all-terrain vehicle by any means at all. This is a very nice indoor, flat-level, guaranteed surface toy where you can frequently swap out the batteries. All right, next thing, the motor direction. So many people, they're like, oh, I have my plywood, and I slap 2 wheels on the side, and I gun them full forward. Even with the PWM, it lists. This is because brushed DC motors have a preferred direction that they like to turn. And if this wheel's going this way, and this one's going this way, and the motors are towards the center, the rotors are actually turning opposite directions in order to make the robot go forward. And brushed DC motors work better in one direction than the other. How do you know you're using brushed DC motors? Because you didn't pay extra to be not using brushed DC motors. So you need to watch this. This is just one of those things to watch out for. You know, any kind of encoders or anything will fix this. Don't just vary the power output. First there's the curve, and then there's a thing that as your battery charge changes, it will change. So like you will have it tuned perfectly for a full battery, and then as the battery goes low, your robot will start listing again, and you'll be sad. Don't do that, guys. This is a panda. Pandas are awesome. Okay, now we're going to go on to some bad ideas. Yeah, those were the good ideas, guys. It's going to get great from here. First item, this is a tether cable. Yes, we're from the 90s when we program our robots. Deal with it. So usually this is what you do to program the robot. It's really important that you take the screws out of the tether cable, because how many people here have had software not do what you want it to do the first time you run it? Oh, you guys are full of shit. Okay, so when your software controls a 150-pound robot, that can be awkward. And when you have screwed in the robot to your laptop, that can be really awkward. And you're going to say, oh, Katie, you know, you warned me about this. There's no way I'm going to do this now. There's a fiery ball of destruction that used to be my, expensive equipment. But the reality is that you have friends, and your friends are probably as dumb as you are. And they're going to think that they're helping, but really, they're not. Really, they have terrible ideas. So, just take my word for it. My teams have lost 2 laptops this way. Take out the pins on the tether cable, and everyone's just a happier person. Next item, speaking of shit that goes wrong, you need a big red button that makes the robot stop. This big red button needs to pull the power from the battery to the rest of the robot and full stop it, just like a switch comes open and there's no more electricity anywhere in the robot. It cannot rely on software. This needs to you need to physically disconnect this. You also need one on the robot and one on the driver's side, because frequently it'll stop listening on the software one's near the driver's station, the hardware's on the robot. This is because chasing down your robot to tackle it is awful. See this guy in the back, he's like, why didn't you put a button on there? Don't do that. Just tackling a person's bad enough. Robots are made of metal. As a side note, if your robot weighs more than 100 pounds, I recommend these during debugging. I'm not kidding you. These are actually especially that 4 in the morning, oh shit, we'll just see what it does. It just makes your life better. And I mean, like, you can look dorky, but at least you don't come out with bruises. Next item, this is a set screw, also known as a grub screw. It goes into robots. You can see here, they're being tightened with this little Allen key to keep an item mounted on a shaft of some sort. They're awful. Don't use them. They will shake loose. They will rattle loose. They will fall out. Mr. Yuck says no. Don't do this. Use key stock instead. Key stock is, and this is basically they cut a little notch in the axle, and then they'll cut a corresponding notch in your sprocket or your gear or your whatever, and this little piece of metal will slide in between them, and this is so much better. And my phone's ringing. Okay. This is so much a better way to go. I've met so many people who I know a team once that their set screws failed so often that they just bought a box of cheap drill bits from China, and every time it came loose, they would drill into it and snap off the bit. Like, the lengths that people wind up going to compensate for the fact that set screws are awful are impressive. During competition, you guys are going to be so frantic for time. Just avoid these. This is a bunny. What the fuck is up with my phone, man? Hold on. There we go. Okay. So, next item, reviewing physics again. Velocity is acceleration integrated. Position is velocity integrated. So you might ask, can I integrate acceleration twice and get position? And the answer is yes, you can. Look, I did this formula, this super pixelated formula down here. All right? And then you might ask yourself, so I can use accelerometers to figure out position? Because figuring out where your robot is like a significantly painful and important thing. So this is really exciting. Can I use my accelerometer's position sensors? No. You cannot. This is why. Okay? So you can see, you have to trust me on the math on this, but basically when you've integrated twice, you have CT plus D. If T is time, as time goes to infinity, C times some non-zero constant, your error, as your robot remains on, as time goes to infinity, your error goes to infinity. This is, yeah, hooray! Don't do this! So many people have tried, and they just don't do the calculus out on this, and they're like, I almost have it working. It works when it boots up. I just have to debug it. It's really hard to watch. So please, guys, this is a cat. All right, these are potentiometers. You turn them. They have basically a resistor that's in varying thickness as you go through it. On the one side, the resistance is thin, and the other side, the resistance is thick. They will calculate your position on rotation. One thing that's important is they have a limited number of turns. Don't put this on your wheels. So they're like, they figure it out pretty quick, but it's really sad to watch. So don't do that. This is for robot arms and for other things that have a limited range of motion. Audio potentiometers, which are like the potentiometers that you find in your speakers, are bad because audio drops off logarithmically. And unless you would like to do math to de-logarithmify, that's a word, your inputs, I'm really sad that I had this fantastic photo of this rookie team that had a driver control station where they just marked off the positions of their arms 1, 2, 3, and it goes like 1, 2, 3, just don't do that. No, don't do that. Buy the right potentiometers. You want linear potentiometers. Next item. Potentiometers are held on with set screws. As previously discussed, set screws are awful. So find something else, find anything else. This is one of the few pseudo-legit uses of a set screw because you really don't get a lot of choice with a lot of manufacturers. But once again, don't use this. If you cannot find something other than the set screw to lose, at least make sure that there's no significant amount of torque or speed that's going on here because these will slip. Next item. So optical encoders are there's no interesting pictures. This is kind of, so optical encoders are essentially black and white stripes, and you have, a little sensor that will be like, I see white now, I see black now, I see white now, and you have these arranged around a spoke, and as the wheel turns, it'll change from black to white to black to white to black to white. People whine that they don't want to make these. If you're broke, use a Sharpie and a CD. We had one year in competition where they wouldn't permit us to use anything that wasn't in the kit of parts. They gave us some Dreamweaver CDs. We found a use for them. So this is perfectly legitimate. Poor freshman is like carefully measuring out these perfectly spaced black lines, but it will work. You can also order them online if you don't have freshmen laying around. The other thing that's important is, 2 channel, I put the slide in, awesome. So these will only figure out absolute measure, is it's black, it's white, it's black, it's white. If you are going the other way, it won't know the difference. So what you need to do, if you want to know the direction and the absolute value, is you need to have 2 stripes slightly offset from each other. So you imagine them like this as it comes past. If you hit this guy first, then this guy, you're going this way. If you hit this guy first and this guy, you're going this way. Pretty cool. Okay, topping 2 layers of metal. There's so many jokes. So tapping is when you put the threads for your bolt physically into the metal. Okay, sorry, I thought someone was telling me to get off the stage already. So basically what happens is you put the threads into the metal and then you don't need a nut on the other end. This is really handy when you're going into deep metal. If you have 2 layers of metal and you put them on top of each other and you tap through them and then one of the layers of metal rotates, the threads don't line up anymore. This sucks. The preferred solution is just drill a clean hole through this guy and put the threads in the lower guy. IKEA is super pro at this. We actually... Well, yeah, no, not. Like, we struggled this, and we're like assembling IKEA bed. We're like, those crafty Swedes. They figured this out. All right, next item, sprockets. This is a sprocket. Sprockets interface with chain, okay? These are gears. Gears interface with gears. This is another one of those things that you'll make me cry when you get it wrong. As a matter of fact, I found this image when I searched for sprocket. And I just felt like this needed to be addressed. All right, chain. You all know what chain looks like. Here it is. Chain stretches. I know it's metal, but it stretches. This is because there are little links. You can see the little links, like these guys. Basically, they're little 8-shaped things, and you put a post through the 2 ends of it. And as they wear, the holes get bigger. So chain, as you use it, will stretch about 5%. And people don't expect that because they're not used to the concept of metal stretching, but it really does stretch. So you need to make things adjustable. You need, like, if you have, a sprocket here and a sprocket here, this needs to be in a slot so that when the chain stretches, you can just jam it back and bolt it in again. It's much easier than all of the alternatives that I've seen that make people really miserable. You also need to have a minimum of 180 degrees of wrap on any, you understand what I mean with wrap, is there's a sprocket and the chain goes around, that's the wrap on the chain. Minimum of 180 degrees on anything that is driving anything else. So idlers, you can go with less, but if it's the motor output or like the next stage input that needs to have 180 degrees of wrap. You have scaling issues when you combine the 5% and the 5% stretch and the 180 degrees of wrap. Because if you have too many teeth in your 180 degrees of wrap, you will eventually just randomly get another tooth on your chain in the process of it going around. So if you have more than about 70 teeth on your sprocket, you may want to re-examine something. This is a pro tip for people who just decide they want to manufacture their own sprockets. Next item, these are idlers on a bicycle. This is okay, these are spring-loaded idlers. Basically, it keeps it tense because there's a spring pushing it down. This is okay because bicycles only go in one direction. If the bicycle starts going the other direction, you just yank it the opposite way of the way with the spring, and your idler's gone. So you need to put the idlers on the unloaded side, and you can only have spring idlers on single direction movement. Be cool on that? It's kind of like, I know it's really hard to get a picture that demonstrates that. Okay, this is a honey badger. What happened to this? Oh no! This is my photo of Bob Ross. But apparently he doesn't want to come to DEFCON. So if you paint your robot, one thing we did this one year with some sponsor was like, we're going to donate a free powder coat painting. Powder coat is like super awesome. It's the way they paint cars. It's very, very, very slick. And so we had this on a friction mount for our adjustable chain. And this was really embarrassing, especially to the sponsor who had just sponsored a very nice powder coat job. So yeah, no painting on friction mount parts. Next item is no painting on friction mount parts in general, because now they're thicker than they used to be. And you're never going to get them apart again. You need to do, and the other thing about this is intolerant stack up in general. If this one is plus or minus, like if this piece A interfaces with B, if A is plus or minus, you know, 1/8 of an inch, and B is plus or minus 1/8 of an inch, together they are plus or minus 1/4 of an inch. You don't average these things. You always assume worst case scenario. It's really important. It's really expensive too when you manufacture custom parts. All right, now we're going to go forward to thinking things through the whole way. I really shouldn't have to go through this, but I do. Bolts have a size. So many people, they design their frames to be the maximum legal by competition, and then they have a bolt sticking out, and there's nothing sadder than to watch a freshman rookie team like filing bolts off the side of their robots. Really, guys, just my coach used to say robots grow. So always give your robot about 1 inch on any side for you to fuck up. Bolts have a size during installation. You can see here that this bolt fits, but there's no physical way to put it in. Bolts are installed with tools. And if there's nothing else I can have you take out of this, please repeat after me. I will always have to take my robot apart again. Thank you so much. Things break. Things break all the time. Things break at the worst times. Assume you have to take it apart. Next item. I will have to drill more holes in my electronics board. Yeah, pretty much. Speed holes make the car go faster, man. But quite seriously, this is the reason that you don't make your electronics board out of conductive material. Because, oh my goodness, we're on in like 5 minutes, I have to mount this extra speed controller, let me just take this drill and drill through the metal plate and bolt my speed controller on, and oh look, now there are metal shards in all my really expensive electronics. Use Lexan, use wood, use anything else, guys, really. More issues. You need to access the electrical boards to plug and unplug things and debug things. You need to be able to replace parts in the electronics board. You need to be able to take objects on and off. You need to be able to take the whole board out for when you frantically are drilling holes in the side of your frame because you are over the weight limit. Just be able to take the whole thing out, put it somewhere else, screw with your design, and put it back, get the canned air, dust it off. By the way, canned air saves lives. So, you have to do those final matches, because usually, you have downtime between matches. Final matches are back to back to back. Turn the things upside down, cover and then cover the motors and the cold stuff. And if they don't shatter, it's great. Also, don't cover your high school interns in that, because they have to go to the hospital. We love you, John. It's okay. All right, flamethrowers. These are an awful idea, but you're going to do it anyway. Seriously, though, especially for battle bots, I've watched a flamethrower robot get its ass handed to it by a robot made by middle schoolers made entirely of plywood. These are not effective. They're awesome, but they're not effective. So if you make a flamethrower, rule 1 is you're going to spill your fuel. You're probably going to spill it on your electronics board. A lot of people I know use isopropyl alcohol because it evaporates. That's a great decision, as far as flamethrowers go. Yeah, so just plan on the fact that you're going to spill your fuel at some point. Batteries. Batteries need to be easy to remove. Fire is really bad. Batteries are one of the objects most likely to kill you on a robot because you're frantic, you rip them out, you put your arms across the leads and you're sad. People ask me all the time, what are good places to get batteries? Cars are not a good place. Car batteries are not for running indoors. What? Yes. People are really creatively stupid. So motorcycles have pretty nice sealed lead-acid 12-volt batteries. I recommend those. Those are pretty solid. If you're looking for a slightly better scale, the lithium sort of things, take them out of drills. They're really, really made to be abused. So those are like the two nice. Also, drills, you can just use the charging station made for them. Just like plug them back into the rest of the drill pack and plug them in the drill charger. They're really nice to recharge. They're quite expensive, though. Oh, yeah. So one time, we mounted the battery to the robot with C-clamps. The steel frame robot with C-clamps. And while we were driving around, the C-clamps wiggled out and managed to get themselves over the contacts. I now advise you to use Velcro to hold your battery in place. What? It caught fire. It was really exciting that we hit the big red button and pulled the flaming battery out. It's the other great thing about motorcycle batteries, you can get another one. Yeah, that was a long night. That was 2 nights before ship day. Next item. When you make custom battery packs, things get really exciting. I am informed, I have not verified, that lithium polymer batteries have about the same density reading on an X-ray as C4. So, UPS ground. Flying with robots these things it's basically a bunch of wires with some things covered in electrical tape. It's really, really awkward to explain. Yeah, good battery sources. Once again, motorcycles and drills. Motorcycles are lead acid, they're heavy, they're inefficient, they're cheap. Well, as they go. Robots aren't cheap in general. Okay, acknowledgements for all the stuff I didn't have to learn the hard way. My mentors on Team 360 when I was in high school who didn't kill me for all the dumb shit I did. Eric Stokely and Paul Roush, my former coworkers from NASA, my really, 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 really tolerant housemates, the IRC channel I'm stupid on, my house that I live in, the hackerspace I'm from, and my employer who came and saw the outline of this talk and said, yeah, we'll let you do that anyway. This is another picture that gives the thing. This presentation is Creative Commons by attribution, non-commercial purposes, share alike. And this is my contact info if you guys want to bother me. Do we have any questions? What's up? No. Oh, it's 10 minutes. My bad. I'm out, man. Get that woman another. All right, you guys have been awesome.